So my name is Shashwat, and I'm a software engineer on the Opendoor data platform team. I'll be talking about how we apply computer vision to some real estate problems. A little bit more about myself before we get started. So I've worked at Opendoor for about 5 years, and in these 5 years, I've spent it primarily in the analytics and data space. Currently, I work on the data platform team, and within that, I work on this team called data acquisition and strategy, whose job is to fetch different data sets and use them in interesting, novel ways to power our machine learning models and produce more signal. So before we go into how we actually use computer vision, I want to discuss what Opendoor is, and just to set some context. Opendoor is an e-commerce platform for real estate, and in a nutshell, its mission is to power life's progress one move at a time. The way we try to do this is we try to take the stress out of moving homes. So buying and selling homes, we try to make it as easy a process as possible. Most people here might be familiar with the traditional way of moving homes, which is if you want to sell your house, you put it on the market, you hold open houses, you have strangers walk through your house. Some people will make a bid on your home, and once you find one which is acceptable, you go ahead and close on that. This process can take months and has a tendency of falling through due to all kinds of different reasons. The Opendoor way of doing this instead is you come to our website, you fill out a questionnaire about your home. We ask very basic questions such as the size of your home, number of bedrooms, bathrooms, things like that. And within a couple of days, we'll make an offer on your home. So we'll send you an offer saying, hey, we believe your home is worth between this price and this price. And if you think that's a compelling offer, you can go ahead and move forward with the process with us. We'll go through a couple more steps, and then we can actually close the entire deal within a couple of weeks. That's the premise of Opendoor, and that's what we try to deliver. Once we buy the house, we put it back on the market, and people can actually buy homes from us, and they can make offers directly on our mobile app or our website. So going back to the first part of what I said, we need to be able to make offers on homes which we might not have even seen. How do we actually do this? So behind the scenes, we have a whole lot of machine learning models running, and they make predictions on all kinds of different metrics. There are metrics like what do we think the home is worth? And there's all kinds of other metrics which we try to make predictions on. So I work on the data platform team, which feeds data into these systems. And we work very closely with the different machine learning teams at the company. I just want to quickly go over the tech stack we use at Opendoor, and that'll help describe how we actually build out engineering projects. So for the storage layer, we use S3. That's a pretty standard way of doing things. All of our large data sets live here. Integrates really well with Spark, which is our main compute platform. For all of our backend services, we use Postgres. On the compute side, we use Spark, which is an open source software. It's used very heavily. It's a pretty standard player in the space. We use a managed version on Databricks. We also have a Kubernetes cluster. So if you ever need a single pod or a single node to run tasks, we can use this. We use Airflow for all of our scheduling needs, and that's also a pretty standard way of using Airflow. And then finally, on the analytics side, we use Snowflake as a data warehouse. So all of your analytical queries run on this. On the machine learning space, we primarily use Spark to train our models and process things on it. All of our big data needs are currently met by using Spark. So let's go into what actually goes into making these predictions on home prices. So we have a lot of data sets that we try to leverage. Some of the most interesting ones are public listings data. So if a house goes on the market in any city, there'll usually be a public data feed which tells us when the house went on the market, how many bedrooms, bathrooms, and things like that it had, as well as the list price, the status of the home. Is it pending? Has it been closed on? When all of this happened? This is a very important data set for us because it tells us about what's happening in the market and helps us find comparables to the house we're predicting on. We also use a lot of tax data. So this gives us information about a whole bunch of homes. It tells us very basic characteristics, again, the size of the home. Does it have how many bedrooms and bathrooms it has and things like that. These data sets give us a very good understanding of the home location. And we can use that to find comparables and try to value the home. But where it really gets interesting is the next step. This information will get us about 95% of the way to the valuation of the home, because we can find comparables and find homes which look similar to this one. But the final 5-10%, which makes or breaks this model, is we require the home features. So we actually need to figure out what is custom about this home, what might be different between these two houses, and how might that actually affect the price of the homes. So here I just want to stop for a second and just have a quick thought experiment. Feel free to come off mute and give an answer for this or put it in the chat. But what do you think, which features of a home do you think are actually important and would make a difference to the value of the home? I've mentioned a couple of basic ones like the number of bedrooms and bathrooms, but if anyone else has any, feel free to throw them out. Curb appeal, yeah, that's a great one. If the home is near a main highway, it could be valued less. If it's in a cul-de-sac, it could be valued more. How the outside looks is really important. Location is huge. Proximity to schools, other things like that. Condition of interiors and exteriors, kitchen appliances, these are some of the things which are very important. And that's kind of where I was driving towards. Furniture, paint, all of these things are really, really important. So the condition of the interior and exterior. So within the company, we call these things like kitchen features, bathroom features, features of different rooms. And these are extremely important. Imagine if you had a kitchen with granite countertops versus marble countertops. One of those is actually more expensive than the other. And figuring that out is extremely important for our valuation system. Similarly, what kind of appliances are being used in the kitchen? And used in the bathroom, all kinds of features, is it sloped? Is it a level backyard? All of these things make a difference in that final 10% of the value. Another thought experiment would be, how would you actually extract this data from photos? So for number of bedrooms, bathrooms, we do have structured data coming in and telling us hey, this house was somebody looked at this house in 2023. We believe it has these many bathrooms and bedrooms. How would you extract things what is the cabinet made out of? What are the countertops made out of? That kind of metadata, how would you get it out from the photos? And just to help with this, I have some sample images. So this is an example. These are sample images from a public listing feed. So for all the homes which go on the market, we get pictures like this. Looking at this, how would you, it's very easy to look at this and be hey, that countertop is granite. These cabinets are made out of wood. This is one of the big use cases that we have of computer vision, where we actually pass in images like this, and we get back a structured feed of these are the kitchen features, these are the bathroom features, and things like that. And then we feed that into a machine learning model and use that to make better predictions on the values of homes. So this is one of the first use cases of computer vision within the industry that I wanted to point out. The next one is on the operations side, and this is something we'll go a little deeper into. So we're going to be discussing the engineering and some of the data science behind this model, and we'll go a little deeper into this one. So this use case is basically simplifying repair estimates. So Opendoor owns a lot of homes across the country. So far, I think in the 6 years that we've existed, we've gone over more than 200,000 transactions, and we're active in about 50 different cities across the United States. This means there's a whole lot of homes that we buy and sell, and maintaining those, keeping them safe and ready to be sold, is an extremely operationally intensive business. One of the things that we need to do is we need to actually estimate repair costs when the house is being sold to us. This is also an operationally intensive process, and we'll talk about more about what this means in a second. But about last year, we came up with a project to discuss, is there any way we can use computer vision to simplify this, make this easier for us to use? And the resounding answer was yes. So I wanted to introduce this project I worked on called Enricher. It's a computer vision-based tool, and it's used by Opendoor to process hundreds of videos each day and help us generate repair estimates for each of these homes. So just to give some more context into estimating repairs, part of the traditional as well as the Opendoor way of selling your home would be once you accept an offer, people will come to your house, have a walkthrough, see the condition of your home, and determine if there's anything that needs to be fixed. This part of the process is called buyer repair negotiation. One of the big value propositions of Opendoor is we no longer need you to have open houses. You don't need to let strangers into your house. And in fact, for this part of the process, you don't actually need to let an Opendoor employee into your house. Instead, what we ask from you is to self-record a video of your entire house, show us all of the different rooms, the kitchen, the bathrooms, bedrooms, front yard, backyard, all the different spaces, and send us this video, and we'll use that to determine the estimation of the repair credit. On our end, what we actually do with this video is we come up with a representative set of images which show all of the different rooms in different like angles, different lights from this video that you gave us. And then we use that to figure out how much repair needs to actually be done and what we need to do to this home. As you can probably think, going from this video to a representative set of like images is a process which lends itself really well to computer vision. With some of the new breakthroughs with like computer vision and like image classifications, we can do this like fairly easily. So before we get into this, the tech stack that we use here matches the data stack that we have for Opendoor. We use Spark to run all of these tasks in parallel. So, Spark makes it very, very easy for us to run things and scale horizontally. And we really wanted to build in mind with being able to support hundreds or thousands of home sales every single, week. So scale was a big consideration when we were choosing our tech stack. The next thing we used is FastAI. This is an open source Python library, which allows us to very quickly train pre-trained models and bring them up to scratch to do like different computer vision or even like NLP tasks. For job scheduling, we use Airflow because we already have the infra and everything built for this. And for storing images and videos, we used S3. So let's discuss the data science component of this. I'm an engineer and I work primarily on the engineering component of this. So I'll be diving a little deeper into that, but it makes sense to go over how we actually built the model and what it does. So the model, after a lot of feedback between all of our stakeholders, all of the operators that were working on this, we came down to a pipeline which runs 3 models. The first one basically detects a person in the image. So if our customer is in the image, it could be they've switched the camera to a selfie camera, or the picture actually has a mirror in it, which shows the person. We don't actually want to use these images. We want to discard these images. So if there's a photo with an actual customer in it, we just go ahead and immediately discard this and don't use it. The next model in this pipeline classifies room by type. So we try to figure out, like, is this a bedroom? Is this a bathroom? Is it a kitchen? Things like that. And the last part of this pipeline determines the quality of the room. So we give it a score from 0 to 5, which is a score of how nice we think the room actually is. So this pipeline came after a lot of feedback and a lot of like different like alpha and beta changes. But in the final version, we basically run these 3 models serially on every single image. So every image that we have, we run each one of these models. For how we actually build this model, we use an existing like ResNet 34 model, great starter, a great place to start from. And we train it using supervised learning, and we have some pre-labeled data. So for example, for the second model I mentioned, which classifies rooms by type, we have a whole bunch of rooms where we'd actually manually labeled them as like, this is a kitchen, this is a bedroom, and things like that. And then we used FastAI, which makes it very simple for us to actually train this like pre-existing model and make it extremely good at detecting these things very quickly. We did the same thing with the person model, where we fed it images of people and not people and help train it on this. And the same thing with the condition scores. Once we had this model, there's a lot of iterating on this. So how did we actually test this and make sure that it works and satisfies all of our use cases? Initially, the process was fairly manual, where people would go through the entire video and watch it and determine the repair estimate from that. When it came time to test this model, we actually ran both of these side by side. So we had an actual employee of Opendoor use the video, estimate the repair credit, and then use the pictures Enricher returned, and then also estimate the repair credit. We have a giant sheet of about like 200 different videos on which we trialed this. So we collected a lot of feedback, a lot of things about like, hey, this is like blurry, that might be something. Learned a lot and kept iterating on the models until so the final result that we had ran a lot faster than the manual process, because of course we're just classifying a bunch of images on computers. It's much faster than a human watching an entire video. And it was also more consistent and standardized. So we got similar results every single time versus potentially having, a wide variance of results depending on who actually processed who looked at the video. So after we ran through all of this testing and all this iterating on the model, we determined that the model is ready to actually be used. And we came into the productionizing phase of this. And this is the part I can talk to on a deeper level because this is the engineering side of things which I worked on. So the Enricher, the design for this pipeline is kind of encapsulated by this image. We start from a video of the person's home, and the final thing we need to return is a representative sample of images. We roughly collect about 100 and 150 images, which we believe represents the entirety of the home. So over here, you can see the Spark data frame 1. So all of these are different Spark data frames, and these are like a series of transformations that we go through and a series of ways of processing this data. The first thing we do once we have the video is we actually download it onto the Spark worker, and we slice it using FFmpeg. This is a great open source tool. If you've worked with any kind of like signals data, you've probably used this tool. The first thing we do is we take the video and we slice it, and we collect about 5 frames per second. So we take 5 screenshots for every second of video, and we create the second data frame, which is essentially the same. So property ID and assessment ID are primary keys in this data set. So we basically convert the video into all of the images, and we store them as bytes in this data frame. Every video can potentially give us tens of thousands of images. So if this initial data frame is only like 20 rows or 50 rows, the second data frame can actually be tens of thousands of rows, so much larger than that. And every single row represents a single image that we have. We did this for the next step, in which we actually run the classifier in parallel. So we run about 500 of these classifiers at the same time. So we can run 500 tasks in parallel. And this is where the scale speed up really comes from. Because we can run so many different things in parallel, this task takes very little time. In the future, if we wanted to increase this from 500 to 1,000 or 2,000, we can by very easily horizontally scaling the system. So the next step to go from all of the images is here, where we actually run those 3 models that we just talked about. So we run the classifier on every single image, and we get this classification and the condition score. And that becomes the third step, the third data frame that we have. The final thing is we go from tens of thousands of images for every video into like a sample set of the images we actually want to use. And for this, we use a proprietary algorithm just to like filter out and choose which images we want to use versus which ones we want to discard. The final Spark data frame that we see over here only contains the 100 or so images that we have and the image data as bytes. The next thing we do is we back up all of these images to S3, and then we also push it to downstream services from which our customers can actually consume this data. So there's a lot of stuff happening outside of this pipeline, but the machine learning component of this pipeline is roughly shown on the screen. So I just want to quickly go over some of the tech decisions we made. So we decided to take about 5 frames per second. This was a balance between how many images we want to process and how much detail we actually want to get. We tried using fewer and more frames, and we decided to run with like 5 frames per second. The second thing we decided to do was actually use Spark to run all of the tasks in parallel. This was used for primarily two reasons. One is it's very easy to run things in parallel. You can write everything in Python and it becomes very simple to use. And two, because we had a lot of expertise in using Spark. Spark is very tightly coupled with all of the infrastructure that we have at Opendoor, and it makes it very easy to launch Spark jobs and run these tasks. Some of the alternatives we considered was for every time we get a video, we launch a new AWS Lambda, and we process the entire the video on each of these Lambdas. The obvious problem with this is, one, we don't actually have this infra set up right now at Opendoor, so this would be adding like a maintenance overhead. And two, if every video is being processed on a single machine, that takes much longer than if we were processing these videos on multiple machines like we do with Spark. We also considered using Kubernetes and using like different pods for this, but it has the same drawbacks as AWS Lambda, where it wouldn't scale as well as using Spark. The last thing we decided, the last big decision we made was storing all of the images as bytes. So one of the ways we could have alternatively done this is we could have stored all the images in S3, so upload all of those images. But as you can imagine, that's prohibitive from a cost perspective. Storing tens of thousands of images when we only want to use 100 can get extremely expensive, and it doesn't really make sense to do. In addition, like the network costs of actually sending the data up and down would just make this like a lot slower. So we decided to actually store it as bytes. We could have also stored this on disk for every one of the workers. But the one big thing to call out here is the worker which actually produces the image might not be the one which processes the image and runs the classifier on it. And for that reason, if we just like create a data frame with a bunch of bytes, Spark can behind the scenes smartly distribute this data across different workers and get the processing done right. So using, after trying out a bunch of different things, storing these images as bytes came out to be the best and easiest way to use this. One more thing I want to highlight while we were building this is we built this incremental processing framework, and we've started using it extremely heavily across the company, across our team. So what this essentially is the custom method which incrementally processes Delta tables. Delta is a open source data storage engine, which is the default when you use Databricks. If you use something like Iceberg, it's a similar version to that, and it allows you to upsert data into large data sets. So I've copied the method definition on the right. And essentially what this method does is it takes in, the table that you're processing, a filter condition, and a process partition method. It filters the data in the table into like only the stuff that you actually want to process, and then actually runs the process partition method on it. This is extremely, extremely helpful for us to use. The process partition method is just Python, so you can run absolutely anything you want on your data sets. A very simple diagram showing this on a high level is kind of here. So we have the full table to start with. We do some amount of filtering to come up with the data frame that we actually want to process. Then we run any arbitrary Python processing on it. So in our case, we were actually scoring images, but we can also push data to downstream services and so on. And then once we actually update the row, we upsert the results back into the original table and mark it as completed and processed. We've been using this very heavily across the team, and it saved us a ton of time and computation and a lot of money also. So just to go over some of the things we did here, it uses PySpark pretty heavily. It uses this method called map partitions and repartition. And this allows us to control how many concurrent tasks are running. So if you have a downstream service, which would get overloaded if you use more than 100 concurrent connections, you can just repartition your data frame to just be like 50 partitions and things like that. And Spark will intelligently only run 50 things in parallel. The map partition method allows us to run any arbitrary Python code row by row on the data. So you can do anything you can do in Python, you can do using this framework. So even outside of stuff that we use Spark for, this is a very good general distributed computing processing framework. The next thing I'll just mention is the filter system that we use can be as complex or as easy as you want. You can just filter on a single column, or you can do more complex filtering. Like I mentioned, we use Delta here. So we use Delta merge to upsert data back into the table. And that's how we figure out like what's already been processed and what needs to be processed. And the last point here makes rerunning any part extremely easy. And this comes from an on-call perspective. One of the things we need to do is maintain these systems in production. And sometimes things like break down and we need to rerun or reprocess different parts of our data. Having this system means all we need to do is modify the existing table, change like the actual table, and then rerun the task and it'll just process for us. We don't need any code changes. We don't need to make any like, PRs or reviews and things like that. So this makes it very easy for on-call to fix issues and reprocess anything that needs to be processed. So this is a method that we use very heavily in the pipeline we talked about. And it's also used fairly heavily for all of our different tasks. I have a quick example over here. As you can see, the filter condition, it's just looking at a column within the data frame, making sure it's not null, looking at another column and making sure that it is in fact null. And we have the process partition method here. All it does is just pushes data to a downstream service row by row. and it's extremely easy to use. And you could have had any Python code over here. You could do anything you wanted with this row. The last thing to mention about Enricher is we have this state table, which basically controls all the processing. We basically have a giant state table, which tells us like, this is where the video is located. Here are the images we've processed, and all kinds of information about where we are in processing these models. If we ever need to rerun any parts of this or redo anything, we can just modify this state table, and it'll take care of actually reprocessing things, redoing whatever we need to. So it's extremely useful to use. And we basically just have this one table which controls all of the processing we talked about. And now for the results. The results of this project were, overwhelmingly successful. Today we're processing hundreds of videos every single day, and we can very easily scale up to process hundreds more. Just a quick reminder: processing 100 videos, roughly each of them are 30 minutes long, results in 900,000 images a day, which need to be classified using the system. And this happens pretty seamlessly on our end. We've been running this in production for the past few months, and we haven't seen too many issues. So as a result, we are in a good shape to process hundreds of videos today, and hopefully in the future, thousands. Yep, and that's all I had to present. If there's any questions, I can take them. I also have some resources, which is opendoor.com and a Medium blog post where you can find more information, or the Medium article, which I mentioned in this.
Fantastic. Thanks for the presentation. So we'll give it a couple of seconds here. If anybody has any burning questions that they want to ask about the presentation, feel free to ask those in the Q&A. Otherwise, you can go ahead and post them there, and we'll archive them, and then we'll pass them along as well. So if there are no burning questions, thanks again for the presentation. Very, very interesting what you guys are doing there over at Opendoor. So with that said, if you want to pass the baton over to Eugene. Well, it does look like we had a question that popped into the chat. If you want to look there.
The house. Would you be modeling the house with the help of CV? Would you mind telling me more about what do you mean? Is it like the actual dimensions of the home?
And then it looks like you've got some questions in the Q&A.
Do you use continuous training? Is it an issue? So we do use continuous training for some of our models. For this particular model, we do not. So we have a preset model, and we use that for all of the videos coming in. Is it an issue that an estimate of the cost of repairs will come relatively long after the video was provided? It's actually not too long after the video is provided. So once the video is actually in our system, Enricher picks it up and processes it within the next 6 hours. So the SLA that we have is actually roughly 6 hours, but in reality, we process it within about like 2-3 hours. So it's not too long after. So yeah, and the next step would be an operations-based thing where a human would take a look at the images and then come up with the repairs. Typically, I think we turn it back in a couple of days, which is like the industry standard. How do you monitor the results of your model? So like I mentioned for this one, we don't have a continuous training. So we trained it initially, and we revisit this every so often. And we rely on our operators to mention any issues with the model. So when we first launched it, there was some videos which weren't capturing images well. We had people reach out to us, and then we iterated and added a bunch of fixes. What are the reasons for bytes conversion for Spark instead of other formats? So NumPy can't actually, NumPy is, runs on a single machine versus Spark, which is distributed. We could have started on NumPy if we were using it in a single machine, but that doesn't work too well with Spark. We just basically needed a way for us to represent the image and pass that along to like a bunch of different machines. Is the inspection done completely through CV, or is human in the loop required? Human in the loop is in fact required. So once these images are generated, we'll pass this on to a human who will actually take a look at them. There's a lot of different things which go into getting this estimate. So for example, different markets have different costs of like actually constructing things or building things. So the human will have the final say on how much the repair estimate would be. So it is human in the loop.
And then it looks like the follow-up to the question in the chat was a virtual model with dimensions.
Dimensions. So this is something where, if I'm understanding this question correctly, it's can we actually come up with like a model of the home? So I'm imagining this as like for all of the rooms in the house, like how big are they, width, length, and things like that. If that's the case, then we do have something in the works where we're trying to do this, where we actually can send people to the homes, and with like breakthroughs in the ways we can capture images. So we can use LiDAR on even like iPhones and things. We can actually try to figure out the dimensions of the home and come up with a pretty good dimensional view. And this is actually a very interesting question that you've asked, because it is a big data quality initiative. The best and only way to know the actual size of the home is to go and visit that house. A lot of the data that we do have gives us a very good, a lot of times it is correct, but sometimes it can be wrong. It's very hard to know for sure what the dimensions of a home is, unless you actually go to the house. So we do have some different projects which are trying to use this, and it would in fact be using computer vision to figure this out.